So we start and finish our last chapter on the same day. Start and finish. Okay, simple harmonic motion, chapter 15 of the book. Let's see, the basic definition of it is oscillatory motion under a retarding force proportional to the amount of displacement from an equilibrium position. Do anyone understand that? I don't.
Harmonic can be a spring,
Uh-huh.
like a block on a spring, and then attached to the board, and then you trying to.
Okay, so you're saying a block on a spring.
Mm-hmm.
Chapter 15, simple harmonic motion, SHM, right? So you're saying that would be one example, right? So you're saying if you stretch the block from a spring, what would happen? What would be the retarding force?
The force is gonna be the tension of the spring. Or
Okay, and then it's saying the retarding force has to be proportional to what?
to the amount of so K times X.
Oh, okay, so as long as the force is proportional to the X, right? Then that's considered oscillatory motion. Why? Why does this produce oscillation motion?
Oscillation.
So, in other words, when you stretch it, this is the amount of the stretch, right? This is what's called the displacement, right? So, the more you displace it, the more the force pulls back. So, right? So then when you let go, it's gonna go. By the time it reaches the middle, isn't it gonna stop when it reaches the middle?
No.
No.
There's
Because the force is zero when it reaches the middle.
There's velocity.
Yeah, and then it starts going the other way.
Oh, okay. So you're saying because it has acquired velocity, it's gonna keep going, right? Because if it comes and the force is zero and it stops, it would just stop there.
Right.
But because in the meantime it has acquired velocity, it just keeps going past that point. So now once it goes past that point, now the spring is starting to push on it the other way, right? The force still stays negative kx, but the x is negative now. And if x is negative, that means the force is positive, right? So then, as it goes past that point, it starts slowing down until finally the velocity is zero. So at the two ends, velocity is zero, right?
Mm-hmm.
But in the middle, velocity is v max. And then, on the two ends, the force is max, F max. And then on this end, F is also equal to F max. Right, you get it? So because it's the maximum displacement. And how about the acceleration? Over there. Well, since F equals ma, right? We also know F is ma. Whatever the force is doing, the acceleration is in sync with that. So if the force is zero, momentarily it's not accelerating. If the force is maximum, the acceleration is max, right? So at the end points, the A will equal it to its maximum, right? And then at the middle, what would be the acceleration? Zero, right? So the motion kind of looks like this if I mimic it with my body. Here I start up, let's say I start out here, right? Zero velocity, but maximum acceleration. So how do you mimic a zero velocity maximum acceleration? Imagine you're in the car and you floor it on the gas pedal, right? After the red turns green. That's maximum acceleration, right? So then you move, but then as you're flooring it, and then you start taking off your foot off the gas pedal slowly, you know? So it'd be something like, so as you take the foot off the gas pedal, as you're going this way, what's happening? Are you still speeding up?
No. You slowing down.
Very tricky question, because I even got him. I got him hook, line, and sinker. So you're the fish and I threw the bait and you made a good mistake. It's a good mistake, not a bad mistake. He said, as you're going this way, you're actually slowing down.
I mean, going in the middle, right? After you pass.
No. As you're going this way,
Oh,
I
you're
said.
speeding up.
I said, are you speeding up or slowing down? You said slowing down.
I thought you said like in the middle, and then after that.
Oh yeah, after
that's
that,
the-
yeah, that, right? So, as you're going this way, you're still speeding up, but the rate at which you're speeding up is slowing down.
Yeah.
So, you see what I mean? It's again a calculus thing. So how do you mimic that? Well, I have to speed up, but the rate at which I have to speed up has to slow down. My God. Let's see if I could do it. It's very hard, right? Because you tend to, when you're trying to mimic it, you tend to slow down, you see? But I should still speed up, but at less and less a rate, right? And when you reach the middle, you should be going your fastest, because acceleration is 0. Then after that, you hit the brakes. You hit the brake, but slowly, you see? Then as you hit the brakes stronger, and when you get to the end, you hit the brakes the strongest. And then at that point, you stop. You see? So that's kind of the physical representation. But then you don't stay there, because then the spring pushes back you out. So then it goes back and forth, right? So then that's basically the idea of oscillation motion. So what are they showing here on the side? You see? So they're doing a hanging mass, you see? When you go like this and you hang mass and then it goes up and down. But then they're plotting the motion of the spring, of the ball, versus time, you see? So you're going like this, and then all the spring is doing is this. But now if I plot that as a function of time, you're gonna go up, this, right? So it becomes literally like a sine function or cosine function, you see, like that, with a certain period of oscillation, you see. So that's why it's called oscillation motion, anything that behaves like this. Would this also give you oscillation motion? What if the force was proportional to x to the square? Or does it only have to be a linear function?
It can be any, as long as the force goes toward the.
Well, wouldn't it be positive?
Would that be, if x is positive, it would give you negative. If x is negative, it would still give you.
Negative.
Oh, it needs to be. If x is negative.
Oh, it needs to
It could be an odd root.
Yeah, it needs to be positive, right?
Yeah, it could be an odd root, but not an even root.
Well, you could just say, let's see, how do we build that into it? You could say something like f is kx squared if x is greater or same as 0, negative kx squared if x is less than 0.
Yeah,
You know,
can
like
say
a
that.
step function,
Yeah.
you know? So that when you're negative, the force pushes, no, it still doesn't work. Oh,
It does.
no, it has to be k absolute value of x squared.
Then it's gonna be the same. You should put.
I want it
negative.
to be positive, right? Oh, no, I need a negative here, sorry. I need
Yeah, it's the same
negative
thing,
here.
yeah.
Then I need
You
a
were right.
negative
To
2,
put a negative sign right there.
Then right there's gonna be kx.
negative 2 squared.
Well,
No, it doesn't matter.
The k is still negative.
Oh, okay, kx squared if x is less than 0. Okay, there you go, yeah. So we would do force is negative kx squared if x is greater than 0, right? So that still will be pulling it. And then when x gets negative, then the force is pushing it as a square function. Yeah, then that works,
Yeah.
you know. And then you could have a cube, right? How about the one that we did in the lab? Remember we did a rubber band? And then we found that the force of the rubber band is closer to a square root function, you know? Or some other power, let's say. I think some of you found that it was 0.7 or 0.8, right? Would that also work? Yeah, we could make it work as long as we just make sure that the sign gives you negative here and positive there. I think it should all be oscillation motion. but it'll be slightly different, right? Okay, so how do we solve the nature of that motion then? So then we say F equals negative Kx, which equals ma, right? And then what's the motion of that? Well, a is the rate of change of the velocity, right? But velocity is the rate of change of the displacement of the x, right? So that means this is the second derivative of that. X double prime. So then you get an equation where it's called a differential equation, right? This
Yeah.
is 0 mx double prime plus kx,
Yeah.
right? So
Do we-
what kind of a differential equation is this called?
Do we take friction into consideration?
Then that'll be damped harmonic
It's
motion.
dampened.
Yeah, then that's
Damping
damped. That's
system.
called damped harmonic motion.
Right. Yeah.
We're doing only undamped here.
Okay. Okay.
Yeah.
Then like it goes to 0 at the end. Finally,
What kind
but
of
still-
differential equation? That's second order.
Second order differential.
Separable?
Do we have to say separable? Second order
Um,
differential
After this
equation.
one, actually.
it's actually no, it's Cauchy-Euler.
Okay, so in this section we discussed the solution of homogeneous linear second order differential equation ay double prime plus bcy in which the roots of the characteristic polynomial are real distinct roots. Oh, I see. Basic concepts. In this section, given an in-depth discussion on the process used to solve homogeneous linear second order differential equation, we derive the characteristic polynomial, discuss how the principle of superposition is used to get. So let's go to, I think this is the one for us. Real roots. So then you say ay double prime, ar squared plus c, solve the characteristic equation for the two roots r1 and r2. Right, y is e to the r1t, y is e to the r2t. Now if the two roots are real and distinct, it will turn out that these two solutions are nice enough to form the general solution. So they give us an example, just to remind ourselves, like if you have a differential equation, y double prime plus 11y prime plus 24 is 0. Then you need some kind of initial condition, right?
Mm-hmm.
Then you say r squared plus 11r plus 24, r plus 8, r plus 3. So that means r is equal to -8 or -3, right?
Right.
So then y of t is going to be some constant e to the -8t, right? Plus c2 e to the -3t. So whatever is that. In other words, the r means what? R is the y prime.
Yeah.
You see, r is y prime. Then what's going to happen? Then
Oh, we took a derivative.
yeah, this is the integral of y prime. So in other words, if y prime is -8, then you're going to have, this is the integral, so then you have to add constant to it.
The
right?
reason why we do that is like we assume that r in this case, y, the function y is e to the r. So that's why the first derivative of y, that's e to the r2. And then the third one, that's also e to the r.
Yeah.
So, and we can plug it in and check.
In other words, this kind of differential equation, what function is there who multiplied by 24 plus the derivative of it multiplied by 11 plus the second derivative of it can be 0. Well, it can only be exponential, because when you take derivative of exponentials, it keeps just giving you back an exponential, you see?
Right.
So that's the idea of that, is it can only be an exponential. So then they're trying to find out what that exponential is. So they take y of t is this, then they take the derivative of that. We plug in the initial conditions to get the following system of equations. So you plug in the initial condition, y of 0 is 0, y prime of 0 is
in this
-7.
case, that's complex. That's why we use Cauchy-Euler in this one.
Yeah, I'm gonna get there
Other
just a
formula.
second. Yeah, you're right. So then,
If
after
it's
that, you
complex, we
solve,
can always
then you
make
get
a
y
plus,
of t is
BI
7/5.
into
And you could always check,
series,
but
which is
after you
Cauchy-Euler.
solve something, you could say, does that really solve that? Then you go back and you take the derivative of this, you take the second derivative of this, then you apply it back into the differential equation. So with differential equations, things, you're never at a loss of saying, oh, does it really solve? Well, you can just check to see if it really does solve that, you know. So then they do another one here. So in our case, the only difference is that we're missing the middle term. Would the same method work for our case? The same method? If we're still missing the middle term, we don't have the first derivative. We have a second derivative and the actual function. We could either take this method or a different method. I think that's the one you're referring to.
What I prefer is like I always like to derive things. So
Have you taken differentials?
I've done that.
Yeah, you see, the more math you know, of course, you're at an advantage. But even this method should be able to work for us. Let's say if I just followed that method, what would I do? Can't I say x, let's see, how would I say, AR squared? Well, in my case, it'll be MR squared plus KR is 0, right? If I'm just following literally those steps.
Oh wait, so
Professor, there wouldn't be an R. 'Cause
Oh no, there wouldn't be an R, you're right.
you're gonna get rid of
MX double prime plus KX?
no.
first one.
Oh, because the R is only the,
This R is only for the y prime, and then R squared is y double prime.
oh yeah, Y prime, and then for the Y, there's nothing. Ah, okay, yeah, say right. So then you just have MR squared plus K is 0. Then R squared is gonna be negative K over M. You see? Then X of T is gonna be, I follow that. So then you're gonna have C1 e to the R1T. Oh, because in our case, I just have one R, right?
They were
Let's see here.
complex.
Plus or minus. Or you could even say, we have plus and minus, right? So you could almost say plus C2 e to the R2T, and then my two solutions is positive square root of negative K over M, and then negative square root of K over M.
Yeah.
Right, of negative K over M, right? So I actually do have two potential solutions. So then what is this? Well, square root of 1 is I, complex number.
That's right.
So then you have I square root of K over M,
Mm-hmm.
negative I square root of K over M.
Okay.
So literally just following the same steps as we did for that differential equation. Then you say X of T is some constant e to the I square root of K over M plus C2 e to the negative I square root of K over M.
No,
There should be a sign.
the case.
Yeah?
You know. Wait, so
So your roots should be alpha plus or minus I beta, and then
Well, okay.
Okay,
Then
so
we're gonna
then the
use
solution-
then we're gonna use that theorem.
Oh.
Because when you have e to the imaginary number,
You
how
have-
can we change that to a sine cosine? Right?
it's, yeah.
Well-
What is that thing called, that identity?
Oh, you guys
E
have
to
that?
the I theta, what is that called? Cauchy? Huh?
It's
Don't tell
Um,
me now, math finals, nothing.
Is this your differentials final?
Yeah.
You're in differential equations?
Yeah.
it's
Oh,
Cauchy
you see
only.
that?
I didn't expect to see this.
It's
You
Cauchy
you were
only,
like,
so-
oh my god, but he never covered the applications of differential equations? You've never seen this?
No, like we didn't cover the physics portion of it.
That's
It's-
bad, no
it's
good.
really
They should
the
cover a little bit at least.
Yeah.
From all that, yeah, I know how to like do all like.
You know how to solve it, but you don't know why it's used for.
Not in real life applications.
All math should be related back to, you know,
So-
most of it should be related
It's
to
Cauchy
applications.
Euler, so
Cauchy Euler? If
Yeah.
I do that,
it's Cauchy Euler.
just go for the audience so they can see. Euler.
It should be C1 times e to the RT or e to the alpha t and times cosine beta t. I remember.
I'm just looking for that equation, e to the I theta is.
Right here,
cosine
right here.
theta,
Yeah, yeah.
No, it's
where-
alright.
No?
wrote
There
down.
is
That's
This is too long. I just want to see the equation. E to the I theta is cosine theta plus
Yeah,
I
that's
sine.
Euler's identity.
It's called the Euler identity?
Yeah.
Okay, Euler identity.
Or Euler formula. 'Cause I think the identity is the identity is the one that's already used from the formula. It's Euler's equation.
Oh, Euler's equation. Okay, there you go. That's what we're looking for. Leonard Euler, 1707 to 1783. Okay.
Should we count your
Nothing? Oh, there it is. Euler's formula in complex analysis. Okay, there you have it. E to the, this is so important. E to the ix equals
cosine x,
cosine x plus I sine x.
I sine x.
What's the proof of this?
It's the Taylor's like.
Taylor series
Taylor's
expansion
same
on that?
cosine and the sine, yeah.
Oh,
And
yeah,
then
yeah,
you
yeah,
have the
yeah,
same
yeah,
sign.
yeah, you're right, Taylor
Yeah, yeah,
series.
yeah.
But maybe an informal proof can be, you write e to the negative ix cosine x minus I sine x, then you just multiply them, right? What's e to the ix times e to the minus ix? E to the 0, which is 1. So if I multiply these two, it should give me 1. If it does, then it works. So without going into the Taylor series stuff, right? So cosine x plus I sine x, right? Because just in case your 7th grade nephew is telling you, I'm learning about Euler, how do you prove this? And then you say, okay, I don't want to give you the Taylor series explanation, but I'll just do a little shortcut. You show them this one. So cosine squared x, what? This is a plus b times a minus b, right? So a plus b minus a, so a squared minus b squared, right? I love that. What happened? Cosine minus I squared is negative 1.
Plus, yeah.
Plus 1, right? So cosine squared x plus sine squared x, that is 1.
Yeah.
So informal proof of Euler's equation. Now could it be, why can't it be sine x plus I cosine x? Can't we reverse them? Sine x plus I? Then it'll be sine squared minus I squared cosine squared. Right? In other words, if we flip them, would it work? Huh?
Because it's still sine squared plus.
Yeah, then it's still sine squared plus cosine squared, right? Okay, therefore we need, the reason it's not that is because of the Taylor series expansion, probably. We can't say sine x plus I cosine x, it doesn't work. If you do the product, it works, but it doesn't work in terms of the other stuff, right? Okay, good. So then the solution to this is going to be what? X of t is going to be C1. So then we break this up into cosine of what? Square root, let's see. Oh no, there should be a t here in my answer, shouldn't there? Square root of,
Yeah,
am I missing the t? Where was the t?
well, I think you just didn't write it from the equation.
Oh, I just didn't write the equation here, t. So then it's just going to be cosine of square root of k over m t, right?
Yeah.
Then it's going to be plus I sine of square root of k over m t,
That's it.
right? Plus C2 cosine of square root of k over mt minus I sine of square root of k over mt, right? But then now we're going to argue that the imaginary component, let's see here, I sine, the imaginary should not exist. In other words, it should be that C1 and C2 are the same actually.
Yeah.
Because this is there should be, we're only looking for real solutions to this, not imaginary, right? So in other words, for this to work, C1 needs to equal C2. Then what's going to happen? So they're both C1. So then when you multiply this here, this times this times this, I, this times this, negative I, sine, right? They cancel each other, then what happens? Only the real answer remains. So then you got your solution, there you have it. Some amplitude, this is gonna be 2c1, but we can just call that A cosine of square root of k over mt. That's the solution to our differential equation. Second order differential equation where the linear derivative is missing, the first order derivative.
Wait, what happened to the signs again? What, you said they got cancelled out?
Yeah, because I sine, they got cancelled out. Because C1 times this, C1 times the negative, because we impose real solutions only to our motion, not
But
imaginary.
in that, it should be C1 cosine.
Yeah, I just called it amplitude because what that means is the greatest amplitude of the motion. You see,
Yeah.
this is amplitude.
Great.
A, negative A. You see? So this is the largest that this can be is 1. That means that number in front of it is the amplitude of the motion. You see, of the displacement. Now, what does this mean? This factor, square root of k over m.
That's omega.
Omega, no?
We call that omega. It's radians per second, right? Omega is square root of k over m, and it's the same thing that earlier in chapter 10 we called angular frequency. But in that application, it's more like a cylinder that's turning. We say this is theta, and the rate at which omega is the rate at which the theta is changing, right? So when it's a cylinder, we talked about rotation, right? And this is the rate at which the angle is increasing as you go down, right? As the cylinder is rotating. So that one is called also angular frequency. Well, it's more called angular speed. And it's also in radians per second. It's the angular speed of something that's rotating, right? Here it's a slightly different meaning. It's the angular speed of something that's oscillating in radians per second. Let's prove that it actually does have units of radians per second. How can we prove that?
That's still angular.
It's
Velocity.
angular, instead of angular velocity, it's
Velocity.
angular frequency. You see? Omega.
Isn't that the frequency that's omega over 2 pi? So that one still, stays the same. Like it's.
I would call it angular frequency, and then the frequency is omega over 2 pi.
Oh,
right?
two different things.
So then you have here omega is equal to 2 pi f.
Uh-huh.
This is cycles per second, and this is radians per second. You see?
Yeah.
So this
That's
is
why it's
rad per second, and the frequency is cycles or revolutions per second.
Yeah.
But then since each cycle is 2 pi rads,
Yeah.
right?
Right.
So when you multiply cycles per second or revs per second by 2 pi, you're gonna get radians per second,
But
right?
yeah, radians.
Yeah, so the way that we write this, x of t, we write it a cosine of omega t, and then we add a phase angle to it, just in case that the object doesn't start, it starts somewhere else, you see? Or we could do this solution, x of t is a sine of omega t. Can both of them solve that differential equation? Yeah, the cosine or a sine. Okay, and then omega is equal to square root of k over m. And then what's the frequency? Frequency is the omega over the 2 pi, right? So it's just going to be 1 over 2 pi square root of k over m. And then what's the period? Period is how long the motion takes to repeat itself, right? So the period is going to be the opposite of that. 2 pi square root of m over k. Yeah, so the period is going to be 1 over the frequency in units of seconds. So if we go back to that first one, let's see here. think it was on the side here somewhere. Oh, you see here? So visually, what would the period be? Yeah. So this block, let's say the spring starts here, and it's starting to move up initially. So you see it goes up, 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 up. When it reaches the most compressed position, then it starts going down. Then it reaches here, starts to go down. Then when it goes back up, so now that's one, we can consider that one wavelength, even though it's not a true traveling wave, right? But we can consider that one wave of the oscillation, one complete oscillation as a function of time. So the period is going to be the time that it takes to go from here to here, or to go from here to here, or to go from here to here. You see? The period is how many seconds it takes to go from some state, repeat the cycle until you come back to that same state. You see? The time from here to here, from here to here, from here to here. You see? From here to here. That's the period. You see? And that's going to be 2 pi m over k. And then it's up to you whether you want to use a sine function or a cosine function. The only difference is that it's going to change the phase angle. Now if we go back and relook at that differential equation, we can say, how else could we have approached that? Well, we could have approached that differential equation just by saying you have mx double prime plus kx is 0. I didn't necessarily have to use that e to the rt plus e to the minus rt. I could have just said, to start out with, I could have said, the only function that can solve this is a sine or cosine function. I already should have known that. You see, why? Because only sine function or a cosine function has a second derivative that's equal to itself. You see? Well, exponential also does, but exponential, even the first derivative is equal to itself. You see? So that's why the exponential is the general solution. You see? E to the rt.
But that's why.
But if you say, what function is there whose second derivative is equal to itself, but not the first derivative? Then it's got to be a sine or cosine, because the derivative of sine is cosine, but the second derivative of sine is sine. So you see, you say a sine of omega t. Then you take the first derivative of that, a omega cosine omega t. That becomes your velocity function. Then you take the second derivative of that, negative a w squared sine omega t. That becomes your acceleration function. You see? Then you put that into your differential equation.
Mm-hmm.
Then you say m times this plus k times that must equal to 0 for all values of t to satisfy the differential equation, right? So then what would happen then? The sine omega t factors out, the amplitude factors out, then you have what? Negative m omega squared plus k is equal to 0. So this is the more specific approach to this differential equation that's missing the first term, the derivative term.
Mm-hmm.
Then you say omega is equal to square root of k over m. There you have it.
But you're missing the initial condition of that.
Yeah, then we're going to add that to the function. And then we're going to say a sine of square root of k over m. Then we always add an initial condition, fudge factor it's called, you know, just to solve for the initial condition.
Yeah.
Can I say?
Finally, yeah. Mm-hmm.
Now, what other kinds of harmonic motion is there that's proportional to the displacement? Oh, before going to that, what if the force was, let's say, nonlinear? Would that be easy to solve? Let's say the force was proportional to the cube. I'm making it the cube so that we don't face that positive-negative issue. right? So when x is positive, it's positive. When x is negative, it's negative. Let's say you had a weird spring that was proportional to the cube. Could we solve that differential equation, or much harder?
You can mimic like how it goes, like, because
That's probably a very hard differential equation to solve, right?
that's very hard to solve. Like,
A function whose second derivative plus the function cubed. Oh, that's very hard to solve. Is that going to be a sine function?
no.
Oh, then maybe it's not even oscillation motion. I guess it has to be linear.
It can be something like,
Yeah.
it's like,
I don't think it would be, I don't think you'd be able to do it with the other method that you were using in the beginning.
Yeah, I don't think that's that method.
That method wouldn't be able to be applied to.
So I guess the method works only for when these are linear, right? Not squares or anything.
Yeah, the last term always has to be just x or y.
Because sine, this will be something like sine cubed of x, and then this will be sine of x. Well, how can sine of x plus sine cubed be always zero for all values of t? You can't have that. How can a sine function add up to a sine cubed function and always cancel each other? You can't have that. So it's not going to work. It has to be just linear. See? So that solves that, right? I mean, as a differential equation problem, it might be interesting, but there's no physical representation. So does that mean when you stretch the rubber band and let go, you're not gonna get oscillation? If it's power like 0.7? We gotta try it, I guess. Something tells me that it might still oscillate. But maybe a different kind of solution, very different, you know. That's for computer programming to do. Can a computer program solve a differential equation? That's our resident computer scientist here. And then see if the computer program can solve any value of differential equation, any power, you see. Put that in there. It should be able to. See, computers are dumb, but if you know what you're doing and you can program it correct, then you should be able to solve anything, really.
Well, with the rubber band, like the way that we did it in the lab, I don't think it would oscillate. But maybe if it was holding between two objects and you would pull it back.
Oh yeah, something like that. Maybe you pull it back and then it goes like this. Yeah, the way we were doing it, we were just hanging it.
Yeah.
Probably not, yeah. But something like a horizontal motion. Okay, what other kinds of motion is there whose retarding force is linearly proportional to the displacement? Those are going to be what's called the simple pendulum and the physical pendulum and the torsional pendulums. So that's in the category of pendulums. There's a whole history of pendulums because Galileo was the first one to experiment with pendulums. Galileo, imagine him. So there's a good whole history, right? So in this case, what's the restoring force that's bringing this back? Keeps going back and forth. You see, Galileo Galilei. So here's the first one. From the first scientific investigations of the pendulum around 1602, the regular motion of pendulums was used for timekeeping and was the world's most accurate timekeeping technology until the 1930s. It's a pretty long time. The pendulum clock invented by Huygens in 1658 became the world's standard timekeeper, used in homes and offices for 270 years, and achieved the accuracy of about 1 second per year. It was only off by 1 second per year. Before it was superseded as a time standard by the quartz clock in the 1930s. Yeah, so maybe your extra credit report, you could do it on that. Timekeeping, and what does it mean? How does the quartz clock work? Do a whole nice history of that and the physics of that. Historically, they were used as gravimeters to measure the acceleration of gravity. The word pendulum is New Latin from the word pendulus, meaning hanging. Oh, okay. And they go into the whole history. See? So now, the period of oscillation, they say, is what? That's our goal, is to derive this equation. The period of oscillation is 2 pi square root of the length of the pendulum divided by gravity. But it only works if the angle is kind of small, like less than 1 radian. Let's see. So how many degrees is 1 radian? 50 something degrees, right? So it works only, they usually say it works if the angle is like 10, 15 degrees, the equation works better, you know. So why is that? Well, let's see. This is called the simple pendulum. So then you write the equation down, and then you say, this is theta, this is mg, right? So what's the restoring force here? It's actually a torque. R crossed into mg, right? Torque is equal to the moment of inertia times alpha. So in this case, it's not really technically a force that's bringing it back, it's a torque. So you say R mg times the sine of that angle, which is the same as that angle, right? The angle between the two. So R mg sine of theta, and that's a negative restoring torque because it's going to bring it back, and that's equal to the moment of inertia times the second derivative of the theta, the alpha. Remember, alpha was the derivative of omega, and omega was the derivative of theta, right? So then you have here 0 is equal to I So this equation works whether or not you're dealing with a simple pendulum or you're dealing with a physical pendulum. Physical pendulum. Physical pendulum is, let's say, if you have a rod pivoted about the end, then it's going back and forth. You see? But then the weight is concentrated at the center of gravity, right? So then what's my R? Then the R will be half the length of the rod. You see? So the idea is always the same, but for a simple pendulum, we're assuming that the string has no weight and this object almost has no dimension. So it's kind of small, so therefore it acts like a point object almost, right? So when we apply this to the simple pendulum, we're going to get a specific equation that just applies for simple pendulums. So what's the solution to that? Well, let's go back to mimic the spring problem. The solution to that was omega square root of k over m, right? So then our solution, we could just mimic over there. But here's the problem. Sine theta and theta are not the same. In other words, try finding a function whose sine plus the second derivative is 0. Can we do that? Well, no. So this one is almost impossible to solve. If theta of t is a sine of omega t, imagine taking sine of sine. Right? That would be the way to solve it. What would be the second derivative? Negative a omega squared sine of omega t plus rmg, and then sine of a sine of omega t. Try solving that differential equation. That would be the general solution to the motion of this. And it would apply even if you're not less than 1 radian, you know. That one is very hard to solve because, I mean, how are you going to start solving it? Find omega, you know. Sine of sine, that's kind of weird.
They find a motion of vary.
In other words, find the omega that will solve that problem. It's very hard. So what we do is we do the Taylor series expansion of sine theta, we say if the angle is less than 1, much less than 1 radian, right? That's why, see, they say much less than 1. So then they say, if that number is small, you start with a small number, then small number cubed is even smaller than a small number, right? So in other words, if theta is 0.1 radians, would it be true sine of 0.1 rad is 0.1 minus 0.1 cubed over 3 factorial plus 0.1 to the 5th over 5 factorial, right? They just keep going. But then is 0.1 cubed much smaller than 0.1? If it is, I can ignore it. Then I can just say sine of 0.1 is approximately equal to 0.1 and just forget all the other terms. If I can, then that's good. Because then I can say sine of theta is just theta for small angles, right? So if you want to make sure if that works, take your calculators, right now, change it to radian mode, change it to radian mode. So in this chapter, you're going to be pure radian mode. Then go to radian mode. And then take sine of 0.1 and see what it's equal to. Sine of 0.1 radians is 0.0098. No, 0.098. Right? So sine of 0.1 radian is going to be 0.099833416666. In other words, how did the calculator even calculate that? When I put sine of 0.1, what did it do? It used the Taylor series expansion. It did this plus this plus minus this. It did that. Can you just keep going indefinitely? Yeah, but after a while, the calculator realizes I'm getting so small that it doesn't change the significance. And then how many digits is the calculator's accuracy? 1, 2, 3, like 12 decimal places, right? So what it goes is it probably goes until it says this one does not affect this number anymore. It only affects the later digits, you see? So if I have 12 decimal accuracy, I'm just going to stop at this term. You see, let's say. And then all that matters is this. But you notice even if we cancel all of this, 0.1 is almost the same as 0.0998, right? Not that much difference. So therefore, for small angles, you can say sine of theta is theta, more or less, right? Then that if differential equation becomes a doable differential equation, it becomes 0. Well, then it completely mimics this, right? Omega something times second derivative plus something times the function is 0. So then what's the omega of that? It's going to be square root of what? Whatever is the something in front of the x, which is RMG, divided by the something in front of the I. Right? Now the frequency is going to be that divided by 2 pi. And then the period is going to be the reciprocal of the frequency. Tomorrow's lab is all on this. Oscillation motion, physical pendulums, and you're going to have lots of extra credits too for that one. So now you have I over RMG. Now if we apply this in particular to the simple pendulum, what is the I of the simple pendulum? The moment of inertia of the ball. So let's say this is the length of the string from here all the way to the middle of the center of mass of the ball. That's considered the length of the simple pendulum, right? So what's the moment of inertia of the ball? Well, if the dimensions of the ball can be ignored, if it's much smaller than its distance to the pivot point, then all that you worried about is the shift amount, right? Moment of inertia of the sphere is 2mr squared. 2/5 mr squared, but the r is so small. But then you shift that all the way to the pivot point. Pivot point. So what's the moment of inertia? 2/5 mr squared plus ml squared. You see? Where that's the shift amount. But then this is negligible for a simple pendulum. Because the definition of simple pendulum is that the ball is small compared to its distance from the pivot point. You see? So then this becomes what? ml squared, right? And then what does this become? R. Well, R is just going to be what? The same as the L, right? Because the torque is the L, right? So then we have here LmG. So then what's the period of oscillation of a simple pendulum? M cancel, ml squared over LmG, LL cancel, 2 pi square root of L over G. Is that it? Yep. 2 pi square root of L over G. Okay, so let's see if we get a string. I'm trying to find some kind of thing I could use as a string. Let's see. See, because you always want to adapt to your situation. If you're at a party and someone says, "We're bored, show us something from your physics class," you want to be ready on the spot. Oh, and then you say, "Yep, I got it." See? And you say, "Anyone, do you have a charger?" Yeah, I have a charger. Okay, let me show you. Say, right on the spot. And you'll be like, "Okay, let's time this, guys." Could this be modeled as a simple pendulum? Is that dimensions of this smaller than the length? Yeah, quite smaller, yeah. So then you say, okay, let's time it. So then you say, somebody get your iPhone. Oh, I don't have my iPhone. Does someone get a timer? Let's do 10 revolutions.
Wait, so 10.
Ready? Go to your stopwatch.
1, 2, 3, go.
Ready, set. Now I'll say go.
Okay.
Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
15.73 seconds.
Okay, so then say what's the answer? Okay, so kind of do it loud so everybody in the bar can hear you. You know? So time is 15.73 seconds. The period is 1.573 seconds. Then you say, guys, what did I forget to do? And everyone's like, what did you forget? No, you timed it, you did everything. Well, now if I want to apply the theoretical, I need the length. Did I measure the length? And then people are going from the corner of the bar. No, you didn't. Even though I was drinking, I didn't see you measuring the length. So then you have to go back and try to remember what you used, right? Then say, anyone have a meter stick? Yeah, the bartender. Right? He needs one in case he gets a customer that's hard to deal with. So then you say, I go all the way to the center of mass, everybody. Okay, let's make it to the center of mass. So that's 65. 65. I'm trying to see, that's kind of what the length was, right? So 65. So then the period of oscillation, 0.65. Change it to meters from 65 centimeter, right? Over 9.8. If that gives us the same answer as this is called the experimental answer. This is the theoretical answer. If it gives you something close, then it worked, you know. So calculate that.
1.618.
1.618, yeah, it's pretty good. because I didn't quite remember how the length I had done. I might have done it a bit shorter, I think. So then that would have been close to that. Perfect. You see? So that means the formula is working when we mimic it as a small object, right? Now if I go like this, does it work? Like a smaller pivot point. So now let's time that.
Right, so,
It's basically, I'm almost like right there, you see?
okay. So
Okay, ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
5.85.
Okay. Oh, let me measure it. So that one's gonna be to the center of mass, it's gonna be about 8 centimeters to the middle of the thing. 8 centimeters. So if I use this equation, 2 pi square root of L over G, right? And then what was my experimental period? 5 point? You said 5.85?
Mm-hmm.
So divide that by 10 because I measured 10 cycles, right? 0.585 seconds. So the theoretical is going to be 2 pi square root of, and then the distance was 8 centimeters roughly, so 0.08 over 9.8. My hunch is that this one shouldn't work that well.
Well, it's 0.568.
Huh?
It's 0.568.
Still kind of worked. It's not bad. Now, what would be the more accurate way of doing this one? Well, now the object is more, dimensions are significantly larger than the other case where it was 60, you know. So then I need the, what's the general equation?
It was
The 2 pi square root of I over mg r, right? So then I need to say the r is the distance from the pivot point to here, right? Because remember, how did we derive the formula? We said this is r mg, right? So then r is always what's causing the torque, in other words. The idea of the r is the torque. So here the torque is due to the weight of the object, which is at the center of mass. So r is going to be from here to here. So that's going to be m 9.8, and then the r is going to be 0.08. Now what's the moment of inertia of the object? It's pivoted about that point, but then that's the moment of inertia of the IZZ, right? The axis that's going like this is 1/12 ml squared plus w squared, right? 1/12 ml squared plus w squared plus, right, this is L and W, right, plus the shift amount, the moment of inertia shift from here to here. So then plus mr squared. And then m cancel. So that gives you, hopefully it'll give us a little bit more accurate answer. So 1/12, what's my length squared? Well, this almost looks like a square, so the L and the W are the same. Does the thickness matter? Let's see, when you're doing this, around what axis is it spinning? It's an axis going through the middle, right? So the dimension along the axis does not matter. Let's say it's this one. Now it would be different if I did this. Yes. See? That's a torsional pendulum, not physical pendulum. It's called torsional. You spin this, but it doesn't last that long because it kind of fades away. That one we can only time like 2 revolutions. 1? No, not even. Yeah, it never comes back. For that one, I need like a more thread, you know, and then I could do a torsional pendulum. Because then the moment of inertia will be this one, going through here. So then this dimension will matter and this dimension will matter, you see, but not that one, you see. Okay, so then, so the length is gonna be 6 centimeters by 6. 6 by 6. Okay, so then you have to put here 0.06 squared plus 0.06 squared plus the shift amount, which is 0.08, over 9.8 times the R, which is also 0.08. Hopefully that will give us an answer closer to the experimental 0.585, whereas this gives us 0.568. You see? In other words, this didn't account for this portion. It almost ignored this portion, and it just concentrated on this. And then you make it a simple pendulum. See, then if you only concentrate on this, what's going to happen? This is going to cancel with one of these, and then you're going to get 0.08 over 9.8. You see? So if you do this, what do you get? But because of the 12, it's not going to change it too much. It's because it's divided by 12. And then this is not divided by anything. So the shift amount still kind of dominates this over that. But it's probably going to be slightly bigger than this, you see? Which is good for us because it'll be closer to this. And then now everybody in the bar will just buy you a drink. Wow, you mean you can get an answer better than that? Yeah, I could, by accounting for the dimension of the object.
Yeah, 0.594.
Okay, yeah, it is closer. Now it's too big, but the idea kind of is shown. You see, this is closer to the actual answer. At 0.594, 0.585, yeah. But here this is 6 instead of 8, you see. So the actual answer should be bigger. It's because you're actually accounting for the dimension, you see. So that's the only difference then physical pendulum and simple pendulum is this object is a thing. So now let's apply the physical pendulum to not just to this. Let's say now the bartender says, "You're so good, you got a whiskey on me, but if you show us another one, you get margarita." Okay. You say, "Okay, anybody have a ruler?" Oh, he already had one, right? The bartender. So now let's say I pivoted about a random point, then I time it. So let's do another timing. And everyone's like, "What? Don't tell me he could also do that." Yeah. You know? So if they don't have a ruler, you could even do it on a marker. You know? But marker doesn't oscillate too well. Okay, ready, set.
Oh, wait. Okay, so.
Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
14.94.
Okay. So this could be like example 2. I pivoted it around the 80 centimeter mark, and the experimental period 14.94. So divide that by 10.
1.494.
1.494.
4.
Okay. Now, can I try using this equation? Well, this one is, you can't even try using that because what L are you going to use? Are you going to use the L from the pivot to here? Are you going to use the total L of the, so the formula just sort of breaks down because you don't even know what L is in this case. You can't put 1 because the edge is 80 centimeters from here. So it's kind of like you're at a loss. Let's just say you tried to use it and you put 1. Let's see if it comes out anything close to the experimental. In other words, we're gonna show just by trial and error that this equation cannot get the answer. Cannot even get close to the answer, right? What does that come out?
2.007.
2 point?
007.
Oh yeah, way, way off. Not even close. Okay, well now, what if you use 0.8? That means you use the length from the pivot to the edge, right? Maybe that's gonna be closer.
1.7. A little bit closer, but still off.
This one is too sad. Your mouth is like this. How do you do that? Both lips are down, right? This one is like the bottom lip is up, then this is still down. So now you say, okay, let me use the distance from the length from here to the center of mass, 0.3. 1.099. Well, that one's even more off. So yeah, basically back to the mouth down. So you see, no matter what trick you try to do to the simple pendulum equation, it ain't working. So you got to do for this one, only the full-on equation works. So what's the m? The m we don't really need. The r is going to be the distance, right? Because it's this mg, so this is r, right? So the r is what? The distance from the pivot point to where the gravity is, because that's what causes a torque on the system, right? So then in my case, it's 0.3, right? Then I is the moment of inertia about that pivot point. So it's going to be 1/12 ml squared plus shifted to there, right? 1/12 ml squared plus mr squared. So the shift amount is the same as the torque for the r. The r is the same. Then the m cancels. And by now, everybody in the bar, like you have a whiteboard and just mesmerized what's going on, you know. Then 1 squared, that's just 1. Then r 0.3 squared. Okay?
The shift demands 0.3, right? Okay.
Let's see what that comes out.
Very close to it.
Huh?
1.526.
Where's my margarita? Come on, guys. Who can make a good margarita afterwards? Right? Nice. But the experimental I get should be larger than that because of friction. The fact that it's smaller tells me maybe I didn't do the timing right, you know. So the experimental is always slightly larger. Okay, so then you can kind of see that they do this is the same equation we have, 2 pi squared of I over mgr. Then they give you the whole history of one of the earliest known uses of pendulum, 1st century seismometer. Wow. Devised by the Han Dynasty. Chinese scientist Zhang Heng. Its function was to sway and activate one of a series of levers after being disturbed by the tremor of an earthquake. See, this is it right here. Wow. First seismometer. It's always nice, read up on history. Even if it's, you don't read very detailed, but it's very inspiring, you know, when you see how these things have taken place throughout the years. It gives you ideas, it gives you inspiration. Read books on on the history of science or the history of engineering, history of computer science. All of these fields have deep, rich histories rooted, you know. Get to know some of the famous names, what they've done. The 1656, I think this is Christian Huygens, right? He's the one that discovered the rings of Saturn, right? And we sent the Huygens probes to Saturn in honor of him. So he's also the one that made this first clock, apparently, using a pendulum. See that? This is a supporting weight, and then the pendulum is bobbing up and down. What's happening in this case? Oh, this is when you go to the Griffith Observatory, you see this, the Foucault pendulum. What does that show? That the Earth is rotating, right? Because the pendulum goes like this, and if you give it enough time, the Earth is gonna spin, so then it starts hitting all the pins. Have you seen that in the Griffith Observatory?
Yeah.
It goes like this. And then the drawing it makes is kind of an interesting function, huh? Almost like those conical functions you learn in Calc 2. Which ones are those? What are they called? Conics? Like R is cosine theta, R is cosine squared theta. What were they called? Huh? Oh yeah, polar curves. It almost looks like one of those things you get. You see? If you take into account the Earth's revolution, and then this is just going like this. So then it's actually gonna make a curve like this. You see? Of course, they're speeding it up in terms of the time. Nice history of all the pendulums. This is a good research project you can do. Temperature compensation, because remember, in physics 2 you learn as things heat up or cool down, the length increases, expands. So then, how do we make something that's accurate timing? What if on a hot day it's expanded, its period is going to change? You see? On a cold day it's shrinking, its period is going to decrease.
Right.
So then how do we account for that? How have people accounted for that in the past? So you read up a little bit about that. Right?
Then that can account for the percent error you get in, because the Earth is rotating. And
The Earth's
you get-
rotating on top, the length is changing as a function of the temperature.
Yeah,
I see.
yeah.
And then they explain the fused quartz watch. Gravity. What's the Q factor? Anyone know? Have you heard of that? That accounts for the friction that you talked about. Because this thing, on the real world, this thing never just gonna keep going. You have to sort of push it once in a while. You see? A little bit of a push. Because otherwise friction is gonna make it go away and decrease. So how can a clock give it the right push at the right amount? You see? That's how I'm doing with my hand. Kind of like how we sway a kid on the playground. So you have to account for the Q factor. The Q factor is related to how long it takes for the oscillations of an oscillator to die out. The Q of a pendulum can be measured by counting the number of oscillations it takes for the amplitude of the pendulum swing to decay to 1 over E of its initial swing, and multiplying by 2 pi. You see? So 36%. Then you count for that by pushing it in slightly. So you can have an accurate watch. Q is MW over the gamma. So it goes, well, and then it gives you a little rundown of the history. Okay, so cool. Yeah, how about a problem like this? Let's go to my, now let's go back to the springs and do some typical type of a spring problem. So go to chapter 15. my playlist. So I've got lots of good videos here too. Oscillation, motion, period of oscillation, helium balloon. I actually did an experiment. I put a helium balloon and it swayed back and forth, and I calculated the period of oscillation. See here? Like that. Oscillation of a pulley with a spring, 2 blocks and spring oscillation, oscillations with a spring and a ruler. I've done all kinds of things. Oscillations in a trough. Let's look at this one. Let's see which one. Oh, okay, this is a nice problem. Look at this. This video illustrates the motion, how to analyze the motion of a block and a spring which is oscillating, but then another block comes and hits it. So you have to account for the conservation of momentum. So then this is oscillating, this one comes and hits it, and it could be an inelastic collision where it gets stuck, or it could be an elastic collision. Then what's going to happen to the subsequent motion of that? You see? Ooh. Ooh, 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 ooh. Do I have a, let's see here.
Skip, yeah.
Let's get the volume a little bit up. With the original block and sticks to it. So it's an inelastic collision. What is the corresponding equation of motion for the system of the 2 blocks together? Okay. Okay, so something like that. Let's see if we could do that, but I'll change the numbers and stuff. Or maybe since that is an example of a inelastic collision because it says it sticks, let's do an example of an elastic collision, right? So then you got a block. We could do some similar numbers. A 4-kilogram block has an equation of, let's just say something similar to that, but not necessarily the same. So x is equal to 0.2 sine of so this is the phase angle, meaning the initial conditions of the problem, right?
Okay.
So then it says at t equals to 0, a 2 kilogram moving at 3 meters per second to the right comes and hits it, right? So at t equals to 0, a 2 kilogram block comes and hits it perfectly elastically. So with perfect elastic, at least it doesn't get stuck to it, so it's not going to oscillate with the block. In some ways this is harder than that, or in some ways it's also in some ways it's easier, because it doesn't become part of the system, you see? But it does impart some of its energy to that. So then the question can be, find x of t, you know, in other words, I'm going to have a new amplitude, right? And then, is the omega going to change if it's elastic collision? Because this block is oscillating at a certain frequency, right? This guy comes and hits it, then goes away. So is the omega of this going to change? No, because that guy doesn't become a part of this system, you see? So the omega will still stay 10t. But then what's going to happen to the phase angle? So the problem is going to say find A and phi. Right? The new amplitude. Right? So this is the idea. You have a 2 kilogram block going at, what was the speed of it? Let's make it, well, we can make it any speed. Let's just say 4 meters per second. So now what's this block doing? Well, in order for me to find out what it's doing at t equals to 0, I could put 0 here for t, then I will know exactly where the block is at t equals to 0, right? So, you know what, let's do it this way, yeah. You know what, let's do it this way, because usually these equations are written like this. Spring is like this. And then this is the 2 kilogram block going 4 meters per second. So then if you put here 0, where is the block? 0.2 sine of negative 0.3. So make sure you're in radian mode in this chapter. So tell me, where is the block when it gets hit by the other block? So put that in. Yeah, Bart, always have your calculator up. You're never resting in the class. Never. There's no rest. Till the very last, as it says, you know, even a game in basketball is never done until the last bell, right? How did the Golden State Warriors come back 3 games in a row from 18 down? Never give up.
Negative,
That's what makes them the champions.
negative 0.0591.
Negative point
0,
951 meters.
0591.
Huh? 0,
591.
591.
Yeah.
So basically it's a little bit to the left of that guy, right? To the left of the equilibrium.
Equilibrium, yeah.
Yeah, slightly to the left. Like 5 centimeters basically, right? Because this
Yeah.
would be 5.9 centimeters. So from here to here would be negative 0.0591 meters. Now, how fast is it moving? And which direction is it moving? So I have to take the derivative of this function, right? What's that gonna be? 0.2, the 10 is gonna come out, right? So it's gonna be 2 actually, right? Cosine of 10t minus 0.3. That's actually more important than where the particle is, where the block is. How fast is it going, right? So then you're gonna have here v of 0 is gonna be what? 2 cosine of negative 0.3. Oh, it looks like that's gonna be positive.
1.91.
Yeah, so that means the object is to the left of the equilibrium, but it's moving to the right. That means it's headed towards the equilibrium, right? This way. So it's 1.91 meters per second, and at that instant, this guy hits it already, right? Boom, elastically. So then what do? Then we do a chapter 9 problem, a basic elastic collision. Momentum initial of the system is equal to momentum final of the system. So what's the initial momentum? 4 times 1.91, right? Minus the momentum of that guy, 4 times 2. If it's an inelastic, then this becomes part of that, then we do it like an inelastic. If it's an elastic, then we're just gonna do 4 times V1 plus 2 times V2. So the mass of this guy times its final velocity plus the mass of that guy times its velocity. And then if one of them comes out negative, that means they reverse their direction, you know. So right now I'll just write it as a positive. Then I'm gonna do kinetic energy conservation. Half times 4 times 1.91 squared plus half times 4 times 2 squared. Half times 4 times V1 squared plus half times 2 times V2 squared. And then you can get rid of the half. Actually, you know what? It's probably better to keep the half, because then you can cancel it with that.
Shouldn't it be a minus in between them?
Oh, no, just equal sign.
Oh,
Yeah, just equal sign. No, the kinetic energy is always added. So this is going to be 2 times 1.91 squared. This one is going to be 4 times 2. And this is just going to be 2, and then this is going to cancel. So you're going to have 2v1 squared plus v2 squared. And then here you're going to have 4 times 2, which is 8. And here you're going to have 2 times 1.91 squared. Right?
Should it be half times 4 and then half times 2, because the mass is 2? two, no? Like on
Let's see.
two
Yeah,
per second.
right.
Oh, yeah, what happened here? Oh, no, I did it the opposite,
Oh,
right?
yeah, it's 2 and 4.
Yeah, I'm trying to hurry. Half
Yeah.
times 2 times 4 squared. Yes, then, there you go. Half times 2 times 4 squared. You know why? Because I wrote this wrong. I should have written
That
it,
changed to 16.
I should
instead
have
of
written it 2 times 4.
Right.
Yeah.
Yeah.
That makes it a 16 down there.
You
So
guess
then it's
not.
gonna be 16.
I think that's the only thing it changes.
Yeah, then you just leave it like that. Plus V2, you can substitute it from here, right? So then you have here 4 times 1.91 minus 8, right? Minus 4V1 divided by 2 is equal to V2, right? So then V2 is going to be equal to what? 2 times 1.91 minus 4 minus 2V1. I'm just leaving it like this for now. Then I'm going to substitute it into here. 2, 1.91 plus 16, 2V1.
Plus
Then
that.
V2, you're going to put that whole thing. 2 times 1.91 minus 4 minus 2V1. Quantity squared. Then put that in the solver. And then it should give you 2 answers, right? And remember, one of the answers should be its original velocity.
Mm.
Okay, so now,
As if they'd never hit each other.
so now it's gonna be here, solve 2 times 1.91 squared plus 16 equals 2x. Oops. One of the answers is negative 2, which is, which one am I solving for? V1? V1 was what? See, I didn't even write down the equation. I should define my picture. V1 I'm defining as the
4 kilograms.
the final velocity of the, let's see here, of the 4 kilogram one,
Right.
right? And then the V2 is the final velocity of the 2 kilogram one. So that way you can kind of see in your picture, okay, that's your defined definition of V1 and V2. So now V1 comes out negative 2.03. And then the other answer that I'm getting is 1.91. Which one is the same as its original answer? The 1.91, right?
Negative 2.3.
So you could ignore that. So negative 2.0. So it reverses direction and slightly increases at that instant. So this guy immediately hits it and it starts going back, right, at that instance. So then now what happens? What's the velocity of this guy? So then you put that answer into this and you solve for V2, right?
.88.
But remember, you have to put negative here. Times negative 2.03. .88. Okay, it goes back, but a little bit slower than itself, yeah. So then V2 is 3.88. Okay, now what does this guy do after that? What is its subsequent motion? What is its x of t? Well, it's going to be something like this with maybe a new amplitude. The frequency is not going to change. Is the phase angle going to change?
No. Wait, at that moment, right? T is 0. It doesn't change at all.
I think it should change.
I mean,
Because all of a sudden, remember the initial conditions was that it's going to the right at 1.91, and it's this many meters before the x-axis, right? Before the equilibrium. All of a sudden, by another block hitting it, you're imposing another initial condition. Now the initial condition is that it reverses direction and is going to the left at negative 2.03. You're imposing a new initial condition on the block. So then how do we figure that out? Let's see here.
But that,
You see, instantaneously you impose a new initial condition. So then what happens? I need to find the amplitude and the phase angle. What's my equation? X of t is a sine of 10t plus phi. V of t is what? 10a cosine of 10t plus phi. Now put 0 into the x for the t. You get what? X of 0 is what? A sine of, you put 0 here, a sine of phi. Then you put 0 into the v, 10a cosine of what? Phi. So now what's your new x at t equals to 0? The x stays the same,
yeah.
right?
X
Because
stays
I'm
the same.
hit, my position is still the same, but now I'm going backwards. You see? So this guy still stays at negative 0.023, negative 0.0591. But then what does this become, the velocity?
Oh, you changed it.
Negative 2.03. You impose a new condition on the block. So now how do we solve for a and phi? I could do like this. We know sine squared plus cosine squared is 1, right? Sine squared phi plus cosine squared phi should be 1. Right? So then what should happen? If I solve for sine squared, that's going to be a squared over this guy squared, right? Cosine squared phi is going to be what? This squared. Oh no, I think I did wrong. Sine is this over that, right? So sine is this guy over that guy. Then I'm going to square that. Cosine is this guy over that guy. That's 1. That's going to be your new amplitude of the motion. Let's see. So let's see here. 0.0591 squared plus 2.03 squared over 100, right, is equal to a squared. Right? There you have it. That's your new condition.
Couldn't you also have solved it just by?
Yeah, you could divide them and get a tangent.
Yeah.
Yeah. I chose to do it this way, then I'm going to take my A, I'm going to put it back here and here, then I'm going to solve for theta. Either way, it's up to you how you want to go about, yeah. So let's see. 0.211. So my amplitude slightly did what? Slightly increased. Yeah, because it got a kick from the other block and its velocity now became slightly larger. So now it's going to have a bigger amplitude. Beautiful. See why I say all mathematical equations, you should do problems like this to fully understand and appreciate all that. Beautiful. A is 2.211 meters. Then you put that into here and you say sine of phi is what? Negative 0.0591 over 0.211. Right? And then take the inverse sine of that.
.283.
Negative 0.283 rads.
Should be negative or?
Well, that's what the answer gives me when I take the inverse sine of negative. But here's what it is. We
Oh, you
have
gotta
to
double check it.
we have to double check it. Which quadrant are we in?
We in,
Negative 0.23 is here, right?
yeah,
Rads. So in that quadrant, the sign is negative.
yeah.
But I want the cosine to also be negative. No, cosine is positive.
Cosine,
You
wait.
see? You see here how the
Sine, that's,
here this quadrant, the sign is negative, but cosine is positive. If
Yeah.
I put this radian
so
in
it should
here,
be in quadrant 2.
yes, exactly. So I should add pi to my answer to be in quadrant 2. Then the cosine is gonna be negative, but then sine is gonna be
Positive in
I gotta be in the.
quadrant 3.
Yeah. As a negative.
which quadrant do I have to be?
Quadrant 3.
Oh, quadrant 3, sine, I want cosine to be, oh, I want both to be negative, okay. I need to be quadrant 3,
Yeah,
yeah, exactly.
quadrant 3.
So you take the absolute value of this answer, forget the negative, then just add 3.14.
So that's why it's, yeah.
Because you've imposed, by colliding with it, you've imposed a new initial condition on the block's motion. You see, so then my final motion of the block is what? 0.211 sine of 10t plus this guy plus that, pi plus that. And then I'm in quadrant 3 now. So 3.423. And then after that, the block will continue doing that's harmonic motion, but the frequency won't change. And then if you watch that video, you'll see what happens if this guy comes and collides and sticks. If it sticks, you solve it like an inelastic problem, but then when it sticks to it, it becomes heavier, right? When it becomes heavier, the omega changes. And see, so then you'll see how I solve that one. The omega changes, the amplitude changes. I think for that one, the omega changes, the amplitude changes, and the phase angle changes. All three change, because you stick to it. It becomes heavier. So when it goes back and forth, it's gonna go slower, you see? It's been a long, good semester, guys. Thanks for the patience. Study all of these material. Continue being lifelong learners. And it was nice to be your professor. Okay, bye-bye.
Where is he?